Welcome to the AI Research Roundup. I'm Alex. Today we are looking at a paper trending on X. This paper was published on December 1st, 2025, about a week ago. It introduces a method called asymmetric advantage-weighted regression that lets real robots learn to actively move, scan, and search so they can handle missing or hidden information much better than standard reinforcement learning approaches. The paper is titled Real-World Reinforcement Learning of Active Perception Behaviors. And, as we will see later, the results suggest a simple recipe for turning limited robot sensors into surprisingly capable information-gathering behavior. Also, the authors shared an official GitHub repo for AAWR. Inside, you will find the core algorithm code, training scripts for offline and online RL, config files, and a toy X-arm lifting task with demo generation and training commands. There is also real robot code in docs, though the codebase is still under construction. Alright. Figure 1 contrasts passive and active perception on a real robot. The left side shows a robot stuck with a single blurry wrist camera view, so the object might be present but remains ambiguous. The right side illustrates an active perception policy that moves the arm along a multi-step search path, probing likely hiding spots. The numbered camera snapshots at the bottom track this sequence, which ends when the robot finally brings the target pineapple into clear view. Well, Figure 2 explains how the method actually trains the robot policy using extra sensors. The top row shows the policy network that only receives the partial observation from the wrist camera and outputs a distribution over actions. The bottom row shows the privileged critics that get the richer training time observation and the action and compute an advantage score. That advantage then acts like a thumbs up or thumbs down weight on each action, and the weighted regression loss nudges the policy toward actions that look good under the privileged critics. Alright, Figure 3 turns that training idea into concrete procedures. The left algorithm block shows offline to online learning, where the critics and policy first train on log data, then keep updating as the robot gathers new trajectories, always using privileged sensors like extra cameras during this phase. The right algorithm block shows deployment, where only partial observations feed the frozen policy, so no privileged inputs are needed. This split makes the method practical for real robots that cannot carry bulky training sensors into the field. So, Figure 4 moves from algorithms to the concrete worlds where the policy acts. The top row shows 4 simulated tasks, ranging from a camouflaged object pick to a fully observed pick and an active perception scene with a cock robot, plus a blind pick tabletop setup. The bottom row presents 4 real shelf-style environments, where robots must search numbered hiding spots in bookshelves, cabinets, and a more cluttered complex scene. Together, these tasks span simple picks to rich, partially hidden object searches. Alright, Figure 5 turns those task setups into learning curves. The 3 panels together show success rate versus training steps for camouflage pick, fully observed pick, and active perception coke, with shaded left regions marking the offline pre-training phase. Across the first 2 panels, the blue AAWR curve climbs to about 2 to 3 times the success of orange AWR and dashed behavior cloning. In the right panel, AAWR is the only method that reaches essentially perfect success, while distillation plateaus and the variational information bottleneck method collapses once privileged inputs disappear. So, Figure 5 compared methods on just 3 environments, while Table 1 lays out all 8 tasks and how they differ. The left columns list each scenario and robot platform, from simulated camouflaged picks to real Franca shelf searches. The middle columns specify what the deployed policy actually observes versus which privileged sensors guide training, such as extra cameras, masks, or true object positions. The right columns report reward style, demonstration count and quality, and offline and online training steps, which together show that the method handles both sparse rewards and modest, sometimes suboptimal, data. Okay, Table 3 reports how the helper search policies perform in the real handoff tasks. The table shows that asymmetric advantage-weighted regression delivers the highest search success and completion in all 4 scenes, while also needing the fewest steps in 3 of them, so it is both more reliable and faster. The bookshelf environments especially highlight this gap, and the complex scene confirms that even with clutter, the method still dominates the baselines and the exhaustive engineered search. So the big message is that asymmetric advantage-weighted regression turns cheap extra training sensors into powerful critics, which then teach a partial observation policy to move, scan, and search intelligently. That recipe makes active perception practical for real robots, not just simulators. That is it for this episode of AI Research Roundup. I am Alex. Thanks for listening.